All right, I'm going to kick off here. Hey, I'm Ryan LaBouve. I'm talking about hunting before day zero. A little bit about me. I'm a founder and CEO of Startup Security, and I enjoy doing disaster recovery, storms without hard drives. Startup Security, which is relevant to the topic today, is we help secure the tools, technologies, and companies that are building the future we want. In practice, this means helping Series A, B, and C startups kickstart their security programs, meaning they have no security hires but have built something worth securing, and so we get to tag in and help. In practice, this looks like a lot of security observability and research from our end. And my background, which is also relevant, I was originally a software engineer, worked for a bunch of SaaS companies. Eventually, I got tricked into being an SRE, which is keeping other people's software running, doing a weird mix of DevOps and sysadmin work. And comfortably now, I've settled into doing security work, which is why I'm talking here. And a little bit about how I like to operate, which will also be reflected in the talk. I like to go first principles up, not big tools down. Really into open source tools instead of using black box tools I don't understand. And I am not afraid to shamelessly iterate and be dumb and figure things out as I go. So some of that will come across. Also the slides code, and I built a range to play with this on because even though a lot of the tools we use advertise being pretty easy to use, or in practice kind of hard to set up for the first time. So I tried to build some VMs with them running, so if people wanted to play with it, they could do that. Also, there will definitely be spelling errors, and I apologize in advance. So today's agenda. We're going to start with a story about my first run-in with signals of compromise, and which informs my philosophy for dealing with them. Then we're going to talk about the philosophy of the signals of compromise all the way to the tactics of how we enjoy handling them, and then some conclusions. So what will you get out of this? If you're a beginner to intermediate person or practitioner, I'm hoping to give you a better understanding of the signals available from Linux and how they can lead to improved situational awareness of the systems you're working with. And if you're more advanced, I'm going to try to convince you that having the ability to ask your system very specific questions without relying on external tools is a superpower, and also tell you about my favorite tools, which are all supported in the mainstream Linux kernel. Also, this is a big topic. As I was traveling and preparing this talk, because I do so to the last minute on all of my stuff, here's my stack of books. So we're not going to go over everything in vivid detail. My hope is that I give you enough details to pique your interest, and then you know kind of where to go for next steps, and I'm happy to talk about this stuff all day. So if it's interesting, please reach out to me. And thanks to the organizers. Okay, so let's get into the story of how I ran into signals of compromise, or how to accidentally discover a 0-day. So, and for the definition here, 0 day is a vulnerability that has not been publicly disclosed. The important details here, if you run into one on your system, that means there's no patch and no easy way to track. And so to redact all details of clients, I used AI to generate this Hyperion Corp, a lovely startup SaaS that we will be hypothetically helping today. And so on this client, our goal was to stand up a firewall around a microservice. This was a critical service. This whole company had been growing fast, and it had one security group and no real consideration for security. And so finally, they decided they needed help securing it. So going into this, our goal was to understand what the service was doing, understand the traffic patterns of the service, and then observe the traffic. And so a little bit of detail, we work with a lot of startups in hypergrowth, and this is the phase where they have enough users that people have given them truckloads of cash. And so they have users and cash. They've been told to build very fast, and as you might imagine, growth is prioritized over everything, specifically, or definitely including security. And so for whatever reason, a lot of companies that do this choose to go with microservices, which is important for us as security practitioners to understand. I'm not here to argue for or against them, but just on some quick why, some leadership napkin math here is if I have a bunch of big problems and I can divide them into problems small enough to where I can hire one team to solve one problem, then I just take the number of problems I have, hire that many teams, and we can build super fast. If you've ever worked at software, you know this is likely not the case in practice, but anyways, we're using microservices. Some keys about them: they tend to be one service that does one thing, or a handful of things, and it's important to understand their traffic. So there's north-south traffic, meaning some of our services talk usually through a load balancer to our users, and other services we have talk more just in between services. For example, typically our email service doesn't need to talk directly to our users, but our other services, like our whatever's resetting the password, is probably going to queue the email service to send an email. And it's very common for large companies to have hundreds of these. So back to our story. Here's just like a napkin example infrastructure. We have a front end, orders API, an admin tool, and then those are more of the customer-facing or client-facing services, north-south. And then our back-of-the-house services, we've got emails, user and authentication service, which is the one we're going to focus on, and then metrics. And so, we can kind of generally understand the traffic patterns here. Zooming into this service we're going to secure together, we expect a lot of east-west traffic, meaning other services are likely needing to ask, like, hey, can user X do action Y? We probably have some amount of maintenance traffic. An SRE or a sysadmin might log in to check something out or troubleshoot an issue. There's probably deployment traffic. This is something we'd expect if you're deploying a new image. And then regular system updates, if we don't have any type of internal way to deliver those, they're probably reaching out to some package service to get that. And so, yeah, again, to zoom in on what we would expect this service to do as a user, so we're replacing orders through this API. If I'm user 1, can I delete order 7? This service needs to say yes or no behind the scenes. There's a Golang service that's pretty thin, and we had the user's database powering as a source of truth, and then a simple Redis cache as a way to kind of store the permissions. And you would expect, some type of network call to this to do this. Nothing fancy going on here. So, as a security expert thinking through, okay, what could go wrong if this is compromised? We could poison the Redis cache, so I could make it so users could do things that they shouldn't do. We could exfil data. If we can get to Redis, we can get a lot of information about user IDs and roles. Or if we can make it further than that and get to the database, we can get user data, which is pretty great. It's an attacker, not for us as a defender. Or we can move laterally to other services. So, got it. We understand the service. We understand the traffic. Our next step is to observe the traffic. And this is really where we ran into our first signal of compromise, which was just a signal at this point. And so in order to do this, we focused on TCP. We didn't expect much UDP or ICMP traffic, so care a lot less about that. And we had this idea for what is the smallest way, or how can we derive the right configuration for this service without raising a firewall config that accidentally kills things that we don't need to. And so our goal from a high level was to say, okay, we have the three-way TCP successful handshake. And what that looks like is a source sending a SYN or synchronized packet to a destination, the destination sending back a SYN ACK packet or synchronized acknowledgement, and then ACK. And so if we simply got the count of the SYN and ACKs and knew the hosts and kind of grabbed the counts, we could develop a general idea of the traffic that this service was using and deploy this configuration derived from data that we gathered. So what are tools that people would usually use to do that? Wireshark's pretty common for trying to observe network traffic, but this wasn't really appropriate because it was in a cloud environment. We could use TCP dump. We could use TCP dump. Originally it was built with libpcap, which is a way that you can capture and analyze low-level packets. And then eventually we found what at the time I'd never messed with BPF or eBPF, which is Berkeley Packet Filter. And it's actually a virtual machine that runs in the Linux kernel that allows you to write programs that you can use to do a lot of things from observability, security, and networking. And so, mainly in this case, we can look at low-level system calls and see TCP traffic. And so, has a lot of interesting guarantees too. So even though it's running in the kernel, it's not dangerous for our users or our systems. Okay, so we ended up doing this when we got this configuration, and we noticed something weird. After monitoring send and ACKs for a week, there was some unexpected traffic. And so there was the RBAC surface was talking to the email service a lot. And there's no reason, and it was talking a lot directly to users. And so originally, these were expected traffic patterns somewhat, but it ended up leading us to discover that there was something deeply wrong in this system which we were able to address. And so this is why we got really interested in the signals of compromise, and I think have a pretty novel take on them. And so the quiet revelation here is we were just tracking increments of a system call. And when I historically had thought about signals of compromise, I was used to a lot of details. But I realized that a small counter revealed enough for us to determine something was wrong. And so the typical axis, if you will, for looking at signals of compromise is there's signature-based detections, meaning, hey, this file name matches a known bad file, this IP address matches a known bad IP address. Kind of evolves into threat intelligence databases, behavior analysis, looking at, this system's acting weird. And then, database learning, so ML, AI, throwing data science, if you will, at your problems. But the thing that was missing for me, with my background from being an SRE, there was this distinction, it was nuance between monitoring and observability. And so monitoring looks like taking off my logs from my web server and looking through them. It's a lot of data. And it is intensive to gather it, it's intensive to look through it and drive any conclusions from it. And then observability, we could track a lot less data, but understand if our systems were underwater, if our users were seeing things that we shouldn't, if we needed to provision more things. And it's, going back to tracking simple counters and very simple measurements let us do good service for our users instead of trying to dig through a bunch of logs. And so that's where I really started to categorize this other axis that I found really interesting in signals of compromise, which is trying to take the normal tools we have and then also introduce this idea of what is the smallest signal I can use or most fundamental signal I can use or the lowest level signal I can use to drive to understand the conclusion or understand the situation. And so, and just to say what I mean by big, and then we'll look at the small signals. An example of a big signal is if I'm going to detect like a C2 like Cobalt Strike, there's some very standard, and this is just like Red Canary docs on how to do this. You can look at patterns of named pipes. You can look at patterns of process executions and patterns of, in your command line, looking at certain invocations. But the problem I have with this is it's just a cat and mouse game, so it's like, if I have I'll just change how I name my pipe, or I'll slightly change this thing. And so you're always chasing a very specific thing that takes a lot of data to gather. On the other hand, what if we took the smallest signal possible and, kind of decomposed what a C2 is doing? And so trying to find a low-level signal, a granular observable signal that we can use to detect something like data exfiltration. They're encrypting data, moving laterally through our systems, privilege escalation. They do a lot of things. So let's zoom in on data exfiltration. This is a concern we have that's really part of our threat model. And let's note, there's very sneaky ways to move files, which is why I think this is interesting to look at it at a very low level and get a high signal read on what's happening. This is moving files through DNS tunneling, which I thought was amusing. What tools do we have? What low-level tools? And we have, on one hand, we have the file system. The other hand, we have the network. These are the two pillars that we can look at. And how do we interact with those? What is the lowest level way we can do that is system calls. I had to go back to junior year of computer science and kind of remind myself what a system call was as I was originally getting into this and really remembering how us in userland communicate with our metal through the kernel using these functions. Well, these functions are events that are really interesting and can drive a lot of data for us if we're observing a system. And so the tools we use here to snoop the system calls, I talked about eBPF, and then I'll show you an example of collecting them with Prometheus. What you can use, these are just the open source tools we use. There's lots of cognates here. Grafana to visualize things, and Prometheus again to query so we can actually compare signals across our systems. And so again, just trying to demystify how to use eBPF and show you some actual examples here, because there's books and books on this. Like I said, it's a VM, and like anything that has this very low level, there's abstractions built on top of them. The abstractions, the two that I use most are BCC, which is BPF Compiler Collection, which is a toolkit that lets us build these, use normal languages we're used to dealing with, and build collections of this bytecode, or BPF tool, which, yeah, I just want to, let's get into actually doing them. And so for Prometheus, for observability, if you're not used to that, it's Prometheus employs a highly efficient, custom-built time series database that's optimized for storing and retrieving large amounts of data. This is like the basic observability tool that you would start off with if you're SRE. So a lot of our companies already use this. And then integrating it into Grafana just builds graphs out of our data we're scraping. And just to show you kind of the query language here, we can do things like that. And so let's dig into file access. So how could we detect if from a small signal that we're exfilling files? So one of the amazing but also frustrating things is everything is a file on Linux. And so you know, your CD drive is a file, every process is a file. So we have to be very specific about how we're looking at this. And so if someone wants to move your file, what are they going to do? How do we know if someone's reading our files? Well, there's a whole table of system calls that are used to interact with files. Of those, there's maybe 4 or 5 that are used when you're reading a file with a program that like cat. And so we can do the same thing we did with synac and say, okay, give me a PID and tell me every time it reads a file. And we can find, you know, if it's our web server, we would expect maybe 1 PID or 2 PIDs to be reading files, maybe 3 PIDs. Maybe we have something looking at system health, our web server, and some other tool that we have installed on every host. So it gets pretty easy to see if there's something that's reading files that shouldn't be, especially at a large answer. And so this is actually really easy with eBPF. There's something called OpenSnoop, which if you go into eBPF, there's a whole toolbox of scripts that they have built. And so you can run this tool and very quickly see if something is reading a lot of files that shouldn't be. And this is a post, Brandon Gregg writes a lot about eBPF. He's one of the original contributors, so I'll mention him a few times. And we can do this access for a lot of similar things: file access patterns, file modifications, file creation, deletion, and even detecting 0-day specifically with eBPF. This is an example of a symleak race attack. And so this attack allowed a user to potentially gain read and write access to any path on the host system. This was related to race condition in Docker. And here is and I use this in air quotes, one line, because it's a very long line, but a one-liner using eBPF, tracing this very specific system call that you could use to know on day 0 that they came out with to help see if their systems were affected. And I believe this, with Greg, he was at Netflix at the time, so they used that. And so that's files. On the other side of the other column we have is network access. And so networking is not something we're going to get into how it works today. I mean, there's a long list. And similarly, there's lots of system calls involved in networking. Even though this is a pretty complicated topic for understanding, let's focus again on the original problem of the 3-way handshake: syn, synac, and ac. And let's do synac. There are 5 system calls for dealing with this, which I links to the slide. You can read about this in detail if you want to. I'm not going to bore you by reading every word now. And we want to, so for this, we can actually focus on one call. So every syn and synac uses the connect system call. And so this initiates the connection to the remote endpoint by sending a send packet and waits for a send packet in response. This is exactly what we want. And in order to do that, it's pretty trivial. So this is a clip from, again, there's lots of scripts, community-driven scripts that can do this. And here's, don't understand the syntax. You don't need to understand the syntax, but it's not very hard to run this one script that does exactly this. And so the output, that was the important bits from SoConnect, and it spits out exactly what we want. And so I'll show you an example of how we, if you're not using the community-based scripts and you end up building some of this tooling on your own, I'll show you an example of how we tie this all together into something that we can instrument, monitor, and alert off of. And so I've named this catastrophe, which is tell me every time that a new process is created on my system, so I can see spikes of processes being created on a system. And so our goal is to collect the stats on new PRIDs created. I want to have complete control over this data, and I want to be able to visualize and query this data. And so how are we going to do that? We're going to start off, this is a eBPF program. The important part here, you see data.pid equals task arrow PID, and then there's this way that a BPF map so that I can read this. Again, I don't write a lot of C, but I do write a lot of Go. And so this is all of the C I have to write. Then I can take this, this is the BPF compiler collection package, and this is just in Go. It's what we write with a lot. There's a Python, Go, pretty much any common language you can use this with. And so we just load, source is the file that we compiled into the bytecode, and then we attach a kprobe for kernel probe on the system call that sysclone is what opens a new PID. And we create a new counter, and we get the payload. So every time this new PID is created, we just increment that counter. And we can see it running on our server. And Prometheus is just, it's kind of interesting the way it works is a text file that has data, and then the Prometheus server scrapes it on an interval. So we can take that after we see it running. We can see the counts incrementing and see them in our graphing tool. This doesn't mean a lot to us, though. We need some way to see if this is working, and so I wrote the most complicated script in the world, which just loops over and does a sleep, which ends up kicking off a new process. So logging into the server and doing this, we can see a massive spike in our Prometheus data. We can see it in Grafana, which a lot of times this is where, every time that Grafana and Prometheus is used is where we queue all of our on-call alerts. And so even though this is a pretty contrived example for doing this, this whole process works and scales to a lot of different types of tools. All you do is customize what type of system call you're tracking, and you can throw it into your alerting infrastructure and make your own tools, which can be very specific to the domain you're working in. So a few questions I had. So system calls are a pretty big topic, but there tends to be on whatever system you're working on, there's a big repository of system calls. And then also, if there's specific programs that you're interested in that you're trying to characterize, you can use a tool like strace and actually look through the system calls that your normal tools are generating, which can help you lead to discover what you want to monitor. And so the other question I had is, how could we subvert this if we were an attacker? And the only thing that I could come up with, and I found a documentation of this, is under extreme loads, the way BPF works, if it gets overwhelmed, as in if I'm an attacker and I'm trying to hide something that I'm doing on a system, I could generate a lot of system calls if you're tracking them, which would overrun the buffers where all of this data is cached before we collect it. But even on that, BPF knows and can alert that that's happening. So again, all the code is there in my GitHub. I'm sure they'll publish the slides, and this is all open source, mistakes and all. If this is something you're interested in, please reach out to me. I love working on this. Yeah, and so just a few conclusions here. The bigger and more abstract our tools get, the more we lose touch with our systems. I remember when I started, I was copying and pasting files over FTP on my web server, and that was it. And now I'm running Kubernetes on a hypervisor in multiple regions. I mean, it's a whole different world, and it feels like after working on so many layers of abstraction, to me it's really refreshing to dive back into the nuts and bolts of how our tools work. And even though there's more overhead today, it's still worth diving in and understanding these fundamentals. We're also, I love big tools. I love dropping name brand tools with big bucks to solve problems. But a lot of times, if your problem is specific, big tool of choice doesn't have exactly what you need to monitor the situation. And so having the ability to actually ask questions of your system on a low level comes up pretty often. And observing small signals can help us solve big problems. Even though this led to 0-day, it also helped us configure the firewall safely. So it's useful for a lot of tasks. Loved eBPF, Prometheus, Grafana, and I think we're going to continue to see radical evolutions and new and interesting tools built with eBPF. Thanks and happy hunting.